Cost sharing. The objective for cooperative game theory is to study ways to enforce and sustain cooperation among agents willing to cooperate. A central question in this field is how the benefits or costs of a joint effort can be divided among participants, taking into account individual and group incentives, as well as various fairness properties. In this chapter, we define the basic concepts and review some of the classical results in the cooperative game theory literature. Our focus is on games that are based on combinatorial optimization problems, such as facility location. We define the notion of cost sharing and explore various incentive and fairness properties cost sharing methods are often expected to satisfy. We show how cost sharing methods satisfying a certain property, termed cross monotonicity, can be used to design mechanisms that are robust against collusion, and study the algorithmic question of designing cross monotonic cost sharing schemes for combinatorial optimization games. Interestingly, this problem is closely related to linear programming based techniques developed in the field of approximation algorithms. We explore this connection and explain general methods for designing cross monotonic cost sharing schemes, as well as a technique for proving impossibility bounds on such schemes. We will also discuss an axiomatic approach to characterize two widely applicable solution concepts: the Shapley value for cooperative games and the Nash bargaining solution for a more restricted framework for surplus sharing. 15.1 Cooperative games and cost sharing. Consider a setting where a set A of n agents seek to cooperate. In order to generate value, the value generated depends on the coalition S of agents cooperating. In general, the set of possible outcomes of cooperation among agents in S, which is a subset equals to A, is denoted by V of S, where each outcome is given by a vector in R to the S, whose ith component specifies the utility that the agent I in S derives in this outcome. The set A of agents along with the function V defines what is called a cooperative game, also known as a coalitional game, with non-transferable utilities, abbreviated as an NTU game. A special case called a cooperative game with transferable utilities, abbreviated as a TU game, is when the value generated by a coalition can be divided in an arbitrary way among the agents in S. In other words, a TU game is defined by specifying a function V, which maps from 2 to the A to R, which gives the value V of S in R generated by each coalition S. We assume V of empty set is equals to 0. The set of all possible outcomes in such a game is defined as V of S is equals to the set such that X is in Rs, such that the summations of Xi, summing for index I in S, is less than equals to V of S. The notion of a cooperative game was first proposed by von Neumann and Morgenstern. This notion seeks to abstract away all other aspects of the game except the combinatorial aspect of the coalitions that can form. This is in contrast with the non-cooperative games, where the focus is on the set of choices, moves available to each agent. Note that in the definition of a cooperative game, we did not restrict the values to be non-negative. In fact, the case that all values are non-positive is the focus of this chapter, as it corresponds to the problem of sharing the cost of a service among those who receive the service. This is by taking the value to be the negative of the cost. Again, the cost sharing problem can be studied in both the TU and the NTU models. The TU model applies to settings where, for example, a service provider incurs some monetary cost C of S in building a network that connects a set S of customers to the internet and needs to divide this cost among customers in S. In practice, the cost function C is often defined by solving a combinatorial optimization problem. One example, which we will use throughout the chapter, is the facility location game defined below. Definition 15.1. In the facility location game, we are given a set A of agents, also known as cities, clients, or demand points, a set F of facilities. A facility opening costs Fi for each facility I in F and a distance Dij between every pair Ij of points in A union F, indicating the cost of connecting J to I. We assume that the distances come from a metric space, i.e. they are symmetric and obey the triangle inequality. For a set S, which is subset equals to A of agents, the cost of this set is defined as a minimum cost of opening a set of facilities and connecting every agent in S to an open facility. More precisely, the cost function C is defined by C of S, which is equals to the minimizations of, where the minimization among all those F prime, which is a subset equals to F of the value of the sum of the following two summation. The first term of the summation is summing for all Fi, summing for all I in F prime. And the second term of the summation is summing the minimizations of Dij, where the minima is taken among all possible I in F prime, and the summation is summing for all J in S. Example 15.2, figure 15.1 shows an instance of the facility location game with three agents, the set A, B, C, and two facilities 1, 2. The distance between some pairs are marked in the figure. And other distances can be calculated using the triangle inequality, e.g. the distance between facility 1 and the claimant C is 2 plus 1 plus 1 because facility 1 connects to B, then B connects to facility 2, then facility 2 connects to C. So with values 2, 1, and 1 as the weight along the axis. So the cost function defined by this instance is the following. C of the singleton set A is equals to 4. C of the singleton set B is equals to 3. C of the singleton set C is equals to 3. C of the set AB is equals to 6. C of the set BC is equals to 4. C of the set AC is equals to 7. And C of the set ABC is equals to 8. Since the monetary cost may be distributed arbitrarily among the agents, it is natural to model the above example as a TU game. An example of a case where the NTU game is where applicable is a network design problem where the cost incurred by an agent I in the set of agents S receiving the service corresponds to the delay this agent suffers. There are multiple designs for the network connecting the customers in S, and each design corresponds to a profile of delays that these agents will suffer. The set of possible outcomes for the collision S is defined as the collection of all such profiles and is denoted by C of S. As delays are non-transferable, this getting is best modeled as an NTU cost-sharing game. For another example of an NTU game, see the housing allocation problem in section 10.3 of this book. As most of the work on cost sharing in the algorithmic game literature has so far focused on TU games, this chapter is mainly devoted to such games. Henceforth, by a cost sharing game, we mean a TU game, unless otherwise stated.